Hello everyone. Today I'm reporting on the outcome of a first project within a series of projects that tries to investigate the role of recurrence and stochasticity in biological neural networks. This first part is entitled Path Classification by Continuous Time, Stochastic Recurrent Neural Networks with Linear Activation Functions. And it is a joint work with Wiebke Bartholomeus and Holger Rauhut from the University of Aachen and Sandra Nessler from the Research Center of Jülich. So in this project, we're trying to classify time series or time-dependent paths using a recurrent architecture. So we have a signal xt that lives in a vector space of dimension, let's say d, and we have a recurrent neural network which is of dimension, let's say n. So we use a pre-processing map u so that we get a new series that lives in appropriate space. So this pre-processing map u is linear and is one of the parameters that we will try to optimize in this architecture. And then the information flows within the recurrent neural network, which is characterized by a connectivity matrix W that we will choose randomly. So this is not one of the parameters over which we will try to optimize. And this is part of a paradigm called the reservoir computing paradigm, which has shown great promise in learning dynamical systems. We will assume that the activation function of the network is the identity in this first part of the series of projects. And we will also assume that the computations are perturbed with Gaussian noise, and the source of this can be either the neurons within the same network or the neurons in the rest of the brain. So at the end of time, we will have a hidden state y, over which we will apply a hyperplane classifier h to get a label v. More formally, what we have is a continuous time model of the hidden state y. Its evolution is described by a differential equation, which tells us the following, that we take the process signal u of x, we add it to the previously computed hidden state y that we multiplied with the connectivity matrix w, and then we add to it some noise, which is of the form increments of Brownian motion multiplied by a noise matrix sigma. At the end of time, we get a hidden state yt. We act on it using a hyperplane h omega b. So omega is the normal direction of the hyperplane, b is the shift of the hyperplane, and then we get a label v to understand the relationship between the input signal x and v. So we act on x using a hypothesis capital H, which has parameters u, the pre-processing map, and omega and b, which are the parameters of the hyperplane. In this simple model, one can write explicitly the solution of the SDE, and the main message is that the last hidden state that we will use to make a decision is a Gaussian random variable that has mean mu xu and the covariance matrix A, both of which we can write very explicitly. So mu is what you get with a noiseless recurrent neural network without noise. It can be also explicitly written. And then the covariance matrix A has the advantages of not depending on the training data, x, and not dependent on any of the tunable parameters that we want to optimize. This is a covariance matrix, so it is positive semi-definite. We have two extreme cases. So we have the noiseless recurrent neural network with when a is equal to 0, and this we call the deterministic accurate regime. And then we have the other extreme when a is positive definite, and this is what we call the stochastic robust regime, and this is regime in which we are interested. In general, you have a competition between these two regimes, the robust stochastic regime and the accurate regime. So since we are interested in understanding the robust regime, we will assume that A is positive definite, and to simplify the formulas here in the slides, we will assume that A is the identity matrix. So we will attack the problem using statistical learning theory, which tells us that we want to minimize a loss function, and we have to choose an appropriate loss function for our problem because the label h of x that we output is random which is different from the classical setting when we output deterministic labels. And a suitable measure of the risk is the probability of having wrong labels, probability of having h of x different from v. So we want to minimize this quantity, but since we are taking a data-centric approach to the problem, we will minimize its empirical counterpart, which is the empirical risk, which we can compute using a sample. And if we find the parameters that minimize this quantity, we will get the hypothesis that is called the empirical risk minimizer. So instead of minimizing the true risk, we are minimizing the empirical risk, and we have to justify that we can do this mathematically. So, which leads us to the first theorem of our project, which tells us that with high probability, the difference between the risk and the empirical risk uniformly over the class of our hypothesis decays like 1 over square root of m, which is the decay rate that you get with pack approaches that uses the Rademacher complexity. And this constant C is also explicit and can be very well interpreted. One consequence of such theorems is that the empirical risk minimizer is the best in class with high probability. That means that with high probability, the true risk of the empirical risk is smaller than the risk of any other hypothesis in your hypothesis class plus a small margin epsilon. So now we have our objective, which is to try to find the empirical risk minimizer. So that means that we have to write down the formula for the empirical risk, which can be written explicitly because we have Gaussians everywhere using the Gaussian cumulative distribution function. So we want to minimize this quantity, which is smooth now thanks to the noise. And if we look at this formula, it has a very nice interpretation. It tells us intuitively that what we want to do is to correctly classify the averages mu when we classify them with the hyperplane with parameters omega and v. That's one. And the second thing it tells us is that we want to maximize the distance of the averages mu xu from this hyperplane, which is reminiscent of another classification algorithm, namely the support vector machine. However, substituting one with the other is in general a bad idea. And here we will illustrate the difference between the two algorithms with a very simple example. Let's say we have green clouds and blue clouds and we want to separate them. In the first scenario on the left, the green cloud and blue cloud are generated with the same distribution, have the same number of points, so you get similar solutions with the ERM and the SVM. In the second scenario, we have some blue points inside the green cloud, and this can be because of one of two reasons. Either the blue points are true outliers. That means that the two classes are not separable, okay? But more importantly, what can happen is that the blue points are mislabeled points, meaning that they are actually green points, but we mislabeled them and we said they are blue points. What we notice here is the SVM considers these blue points as support vectors and therefore shifts its decision based on those blue points, which can be just mislabeled training data. Well, however, the ERM listens to the majority vote because it's an average, and therefore it does not dramatically change its position because of these blue points. And this is one small indication towards the robustness of ERM here. Also, what we can do is to try to separate the input signal from the tunable parameters using two functionals. The functional of the input space is what we call a partial signature, referring to the main signature. So there's some information that is missing compared to the true signature. However, this partial signature, which we call here a feature map, is still a faithful representation of the parts. That means that two parts that are different still have different partial signatures. And then we have a function of the tunable parameters that also look like a signature in the sense that is a polynomial of degree k divided by k factorial. This kind of expression has two advantages, or gives us two pieces of information. The first one is that we can truncate at any order and solve the truncated problem and still get an approximate solution to the ERM. And this is computationally more efficient. So that's one advantage. The second advantage is that it tells us what is the precise information retained by the recurrent neural network. This is the partial signature of paths. So instead of recording what happens to the path time by time, which is an uncountable set, the recurrent neural network retains an accountable set of information, which is the partial signature. And then you can solve both the training problem and the classification problem based only on the partial signature of the paths that are fed to the neural network. Finally, I want to end with the result of some numerical experiments using different noise scales. What we do first is that we check the validity of our theoretical argument that tells us that the difference between the risk and the empirical risk that we draw here in blue is bounded by something that decays like 1 over square root of m, which is here in red. We know in general that this kind of bounds is very conservative. However, we notice that when we increase the noise, this bound is put more and more to the test. The second experiment is merely a training of the network using a larger data set. And we notice that in the small noise scale, we can get a perfect accuracy, 100%. And when we increase the noise scale, the accuracy on average drops, which was something to be expected. Then the important experiment here is the robustness experiment, where we took the data set and started mislabeling the training data. And what we notice is that in the small noise scale, once you reach a certain critical value, the accuracy of your neural network drops in a dramatic fashion compared to the accuracy that it used to achieve before. However, when we have noise that is not negligible, then we notice that the accuracy stays within a certain band. And sometimes what you notice is that the accuracy might even improve. This is due to the fact that we already trained our recurrent neural network using noise. And this is one illustration of the trade-off phenomena between the accuracy and robustness of machine learning algorithms in general. So I thank you very much for your attention, and I look forward to your questions.